Hi, today I'm going to explain the two ways in which trigonometric identities can be derived using de Moivre's theorem. The first way finds the functions of n theta in terms of decreasing powers of trigonometric functions, and the second one finds functions of theta in terms of trigonometric functions of decreasing n theta. Sounds a bit confusing for now, but I'll explain it later on. For a complex number in polar form, de Moivre's theorem states that r to the n cos theta plus I sine theta all to the power of n equals r to the n cos n theta plus I sine n theta. Or when using a modulus of 1, we ignore those and we just say that cos theta plus I sine theta all to the power of n is equal to cos n theta plus I sine n theta. The first method of derivation uses binomial expansion and forms identities by assuming a modulus of 1 and equating real and imaginary parts. So let's say we wanted to find an identity for cos of 3 theta or sine of 3 theta. Then what we would do is we would say cos theta plus I sine theta to the 3 equals cos 3 theta plus I sine 3 theta. Now we know this is true because of de Moivre's theorem, and r is eliminated because we assume a modulus of 1. Now what we do here is we expand the brackets here binomially. And what that gets us is that gets us cos cubed theta plus 3i cos squared theta sine theta minus 3 cos theta sine squared theta. It's a minus because we had an I squared and that's equal to minus 1. Minus I sine cubed theta. And we know that this is equal to this over here, this whole equation. Now what we can do now is equate imaginary and real parts because we know they won't cross over. So looking at just the real parts, we can see that cos 3 theta, cos of 3 theta must therefore be equal to, that should be a cubed, what am I doing? Cos of 3 theta must therefore be equal to cos cubed theta minus 3 cos theta. And we'll make sense of that in a minute because, well, if you look at it, it's actually equal to cos cubed theta, and then the second real part is minus 3 cos theta sine squared theta, right? These are the only real parts, so we know that this statement must be true. If we want to get this in terms of only causes, we can use the identity sine squared theta plus cos squared theta equals 1. And we have a sine squared here, so let's just rearrange for that. We'll find that sine squared theta equals 1 minus cos squared theta. So we could just substitute that into there. And that would give us cos cubed theta minus 3 cos theta multiplied by 1 minus cos squared theta. Right? And now expanding this out, this just gives us cos cubed theta minus 3 cos theta plus 3 cos cubed theta, because we have a minus and a minus, powers of 1, power of 2, add them together, power of 3. So then we have cos cubed theta and 3 cos cubed theta, add them together, and in the end you'll get an identity that looks like cos 3 theta equals 4 cos cubed theta minus 3 cos theta. And here we have an identity, a function of n theta in terms of decreasing powers of the function of theta, because it's cos cubed theta then cos theta. And obviously this can be extended to basically any power, well, any integer power, positive integer power. The same can be done for the imaginary part. So leaving that, we know that the imaginary parts of this equation must also equate. So sine of 3 theta, or more accurately, I sine of 3 theta, but we'll cancel those out on the fly, must be equal to 3 cos squared theta sine theta minus sine cubed theta. And here we can use the same trick of cos squared plus sine squared equals 1, rearrange, and we find that it's 3, 1 minus sine squared theta, sine theta, minus sine cubed theta, and we find almost the exact same thing, that sine 3 theta is equal to minus 4 sine cubed theta plus 3 sine theta, which is the same as this identity, but multiplied by minus 1. And there you have an identity for sine of 3 theta and cos of 3 theta in terms of decreasing powers of sine theta. So that's the first way of deriving identities using de Moivre's theorem. Whatever you want it in, if you want it for 4 theta, 5 theta, 6 theta, you just make that the power and then you binomially expand. The second one uses some standard results of complex numbers in the polar form. So I'll just get rid of this. If you have a complex number, z equals cos theta plus I sine theta, and then you use de Moivre's theorem to find z to the power of minus 1, that would be equal to saying that, and by de Moivre's theorem, we know that that just means we multiply theta by that. So z to the minus 1, or 1 over z, is equal to cos of minus theta plus I sine of minus theta. Now, cos is something called an even function, which means cos of minus theta is equal to cos of theta. Because if you look at the graph, it's symmetrical in the y-axis, which means whether it's positive or negative, it has the same answer. So it means that cos theta just turns into theta. Now if we look at sine theta, sine theta has rotational symmetry, which means if I rotate this, it looks like that. That means it's something called an odd function. And when it's an odd function, sine of minus theta becomes minus sine theta. So this is an even function, this is an odd function. That means I can rewrite this as cos theta minus I sine theta. This gives rise to an interesting fact. If you took z, which was cos theta plus I sine theta, and added it to 1 over z, you would get cos theta plus I sine theta plus cos theta minus I sine theta. And we know that this is equal to 2 cos theta. Oh, sorry. And similarly, if you did z minus 1 over z, you would find that it's equal to 2 I sine theta. Now these are some standard results we need to know, that z plus 1 over z equals 2 cos theta, and z minus 1 over z equals 2i sine theta. But this is just with the power of minus 1. De Moivre's theorem can work for any positive integer. So if we extend this to any positive integer, it means that this identity can also be extended to say that z, let's make some more space here, can also be extended to say, I'll rub that out, z to the power of n plus 1 over z to the power of n equals 2 cos of n theta and z to the n plus minus 1 over z to the n equals 2i sine of n theta. Now, this can be used to find powered trigonometric functions of theta in terms of trigonometric functions of decreasing n theta. It's basically the inverse of the last method we used. So if we looked at z plus 1 over z, right, and let's say we wanted to find an identity for cos of cubed, right, what we would do is we'd cube this whole thing, because this gives us a cos. We know that z plus 1 over z is equal to 2 cos n theta, or in this case 2 cos theta, because n is 1. So we're just going to say that's equal to 2 cos theta all cubed. But now what if we binomially expanded this? Well, doing it gets you z cubed plus 3z squared multiplied by 1 over z plus 3z multiplied by 1 over z squared plus 1 over z cubed. Now, cancelling and grouping all of these would get you something that looks like this. So let's just simplify this. 2 cubed is 8, cos cubed is cos cubed. So that just gives us 8 cos cubed theta equals z cubed plus 1 over z cubed plus 3 times z plus 1 over z. Now, from this identity here, we know that z cubed plus 1 over z cubed must equal 2 cos of 3 theta, and that 3z plus 1 over z must equal, this must equal 2 cos theta, so 3 times that must equal 6 cos theta. Therefore, 8 cos cubed theta equals 2 cos 3 theta plus 6 cos theta. Remember, it's 6 because it's 2 multiplied by that 3. Now all we have to do is divide the whole thing by 8, and we can find an identity for cos cubed theta in terms of decreasing functions of n theta. It goes 3 theta and then theta, the n is decreasing. So you get 1 over 8 multiplied by 2 cos 3 theta plus 6 cos theta. And those are the two ways that you can derive trigonometric identities using Moivres theorem.